Okay, so welcome everyone. So today, we actually get to have the actual welcome lecture instead of what happened on Monday. So, and typically I would have just recorded, lecture one, but since it's the first lecture, I didn't want, like that'll happen throughout the semester. There's going to be times when, hopefully rarely, but there'll be times when I have to. Or I can't live stream at the appointed time for whatever reason, for internet issues or other tech issues or whatever. And typically that'll be taken care of by just recording the lecture or live streaming at some other time. And all these lectures are going to be recorded anyway, so even if I live stream at a time when you absolutely can't make it, it's no big deal. I'm going to record it anyway. But so normally, yeah, I would just record the lecture and post it. But since it was our first lecture, I really didn't want to. I really didn't want to rob you of the experience of, first lecture hype. So anyway, welcome. I'm Terrence. I don't have my camera on because I didn't want to, wherever I put my camera, like if I had it up here in the upper right-hand corner, it would be annoying because I'd want to write here and then it would be covered and then I'd have to move stuff around. I don't know, maybe I'll add my laptop camera or something if you really think it adds, seeing me lecturing to anything. But anyway, so, you're just going to be looking at like the top of my head as I'm writing stuff. So, anyway, so welcome to 461. I got a lot of questions for the semester about the structure of the course versus like 240. The answer to that is that they're almost entirely identical. The only thing is when I teach 461, I usually cover Jordan canonical form, whereas in 240, it is not technically listed as something that's covered, but when I teach 240, I cover Jordan canonical form anyway. So, so for me, it is literally identical. So here's what the textbook looks like. I'll go over that again here in a second. I also got questions about the edition. I don't know, maybe there's a newer edition. I can't remember. It doesn't matter because anything that you need from this textbook, I'll either be writing the homework assignments or depending on how lazy I am, I may post homework from the book, but in order for the edition not to screw you over, then I'll like take pictures of the exercises or something instead. No, I look at the comments. I just periodically look at the comments. So so typically what I will do. So this class is worth 3 credits, but 240 is worth 4. Is that true? Maybe. I don't know. 240 is worth 4. Wait a minute. Is it? They both have one discussion, not 2 discussions a week. So they both have one discussion session a week. So, yeah, maybe that's true. But see, this is a 400 level course, right? So this is a 400 level class. So, it is convenient especially for people that are not math majors that for whatever reason had to need some 400 level math course prerequisite or something. So I think in the past, last time I taught 461 is during the summer, and I think most of the students were actually I think a good chunk of my students were actually grad students that needed it just because it was a 400 level math class, even if it was the same as 240. Anyway, so yeah, so the way that this will go, maybe I'll just pull up the syllabus here. I've already posted the course syllabus on the syllabus page. I'm going to post a more detailed lecture schedule, but not yet, so I'll finish that by this weekend and upload it. A couple of things. So one, I already said in the overview, it is mostly identical to 240. So linear algebra, vector spaces, line and plane geometry, linear equations of matrices, similar matrices, linear transformations, eigenvalues, determinants, quadratic forms, and the Jordan canonical form. The quadratic forms bit, that will be at the very, very end of the class. Jordan canonical form, I'm going to stick that in somewhere in the middle. The textbook, I already showed you, it's Linear Algebra and its Applications, 5th edition. That's what it looks like. It's a really good book, and I'm going to be following the textbook pretty closely. We are going to go in, you'll see when I post the lecture schedule, we're going to go in chronological order and not going to be skipping that many sections. So let's see here. Just a quick. In chapter 1, we're going to be doing everything except 1.10. And chapter 2, we're going to be doing. Oh, in chapter 2, actually, we're going to stop at 2.3. I may do 2. Yeah, I'll stop at 2.4 in chapter 2. Chapter 3 only has 3 sections. We'll do all of those. Chapter 4, and we're going to be doing them all in order too. Chapter 4 will basically do the entire thing all the way through 4.7. Chapter 5 through 5.5. Chapter 6 through 6.5. Chapter 7's quadratic form, it's going to be 7.1, 7.2, and that's probably it. And then after that, it will be whatever fun stuff we're left with. So that's the course. So you see how the textbook is going to be followed very, very, very closely. What else was I going to say? I guess that's about it for the textbook. So for the lecture format, here it is. You're looking at it. So this is the lecture format. I'm going to do this on paper. And that is it'll typically be more readable than that. But this is how it's going to go. I teach a course directly before this, meaning that I only have like a 10-minute window there. I'm going to see how that is. Now that you are here and you see how this works, I'm still going to post an announcement for the first couple weeks of classes. Then after that, I'll just, from that point on, I'll just tell you guys, like, just show up, at the lecture time on the YouTube channel and just look for the stream. I'll probably do that rather than like having actually scheduling the streams. I don't know. I may, if I schedule the streams, I'll let you know. That way you can actually just join it early. But that's typically how it's going to go. So I typically won't get started late. I just did that today because I wanted to make sure that everybody was here. Another thing is, typically I'll only start the stream like 3 or 4 minutes early. So you'll only get like 3 or 4 minutes worth of my sweet jams instead of like a good 10 or 12 minutes worth. But this is going to make it so that if you watch these videos later, because everything's automatically recorded when it's live streamed, so if you watch these videos later, then you won't have to sift through so much dead time. Of course, it's not that big of a deal because it would all be kind of off at the beginning, so it'd be really easy to figure out where the actual lecture starts. But regardless, I won't junk up the recordings with that. Of course, I guess I could just edit it out myself as well too. Yeah, exactly. Smash that like button. Ring that bell, the notifications, right? So that when I go live, you can know, right? In fact, to test out some stream functionality later tonight, I'm going to be streaming something. Or something, maybe. I don't know. Okay, anyway. Yeah, like and subscribe. So anyway, let's see. Any questions? I don't think so. Favorite flavor, Mountain Dew, original flavor. Technically, okay. Favorite flavor, Mountain Dew, is one that's not made anymore. It's Pitch Black version 2, circa 2005. Is amazing. It's literally the best flavor of Mountain Dew ever. Yes, you ask questions through the comments. So stream is a little bit delayed. So it's not super delayed. It's like 10 or 15 seconds. So it might take me a second. Also, if I'm busy writing up something, I may not check for a couple minutes, but I will try to be checking comments pretty often. But yes, you're going to ask questions through the comments. Let's see. What else is I going to say? More about the lecture format. So as I said, all of this is going to be automatically recorded and uploaded to YouTube. In the spring, this happened like 3 to 4 hours after the live stream ended. So if you didn't go to a lecture on a particular day, it was ready for you, 3 or 4 hours later. But for whatever reason, since the summer, this has taken much longer. I don't know if YouTube's having bandwidth issues because of a lot of people live streaming or what, but this has taken like way longer than normal. So in the summer, it took up to like 22 hours for my lectures to appear after they were recorded. So because of that, just beware that you may, if you're opting to watch the lectures later, you may have to wait like a full day to watch a day's lecture. So it can be a little bit annoying. Syllabus list office hours is occurring through live stream as well. Will there be any format provided where we can ask questions verbally? So what I plan on doing, because I've done this before, is so I will have office hours weekly. It will be, I haven't decided when, it will be someday, Monday, Wednesday, Friday. You can pop in, you can ask questions in the chat. I will answer in the chat unless it's a more involved question, then I will unmute myself and take to the paper. Asking questions verbally. So if there is some instance where you don't have some question cleared up through chat, if you wanted to ask me a question verbally, then I can see about you could make me like a private. I could make you like a private Zoom room. We could do like an appointment via Zoom or something. So that's an option if the normal office hours didn't do it for you. So let's see here. Anything else I want to say about lecture format? Yeah, so there's the warning that it's something that I don't have control over, but the lecture could take a while for the lecture to be uploaded to YouTube after it's over. So unless you watch it live, then you may have to wait like a day-ish to watch it. What was anything else I was going to say here? So big thing in bold included on syllabus page. There will be no time-sensitive synchronous assignments during class hours. You're not going to have to show up to some like proctored Zoom room or something. Any assignment that you have in this class, you will have at least 24 hours to do. So homeworks, it will typically be more than that. So homeworks, I will assign homeworks roughly like once every, 1.5 to 2 weeks. Yeah, that sounds about right. Maybe more like 1.5 weeks. So I'll assign homeworks. The way that you will turn those in is so you'll work on the homeworks like you normally do on your paper, and you'll scan using your phone, convert to PDF, and upload it to the ELMS column where it goes, and it will be graded. The exams I will typically upload on some day. I don't have the exam schedule set yet, so when I post the full lecture schedule, that will include an exam schedule. So the exam schedule is going to be, once it's posted, the way that it'll work is like the day before the exam, like maybe the night before the exam, I will post your exam to ELMS where you can have a look at it, and then you will do it and turn it in within like 24-ish hours, probably a little bit more than that, probably more like 48 hours is how it will go. And that'll be that. Basically, the only difference between the exams and the homework is going to be like you're going to have less time to do it, and you're not allowed to collaborate with people. Optional textbook problems for extra practice. That's going to be included on the lecture schedule. So that will be included on the lecture schedule. The optional ones anyway. And then some of those that I've listed as optional, I will actually assign in the homework, or I will write my own homework problems. The other question, so quizzes aren't during a synchronous discussion? No. The quizzes don't really exist this semester, so the only quizzes would be a homework that you only had like a day to do or something. So that if you want to call that a quiz, then that's fine. But really, there's no quizzes. It's just going to be homeworks. Will you talk about homeworks during class, or will it just be randomly posted so we should check off? And no, anything that is graded will have at least one announcement associated to it. So I will always make an announcement when I'm assigning something. There's not going to be anything you just have to like check to see what the announcements are. I will always make an announcement for every assignment. Let's see here. Office hour timings, I haven't decided on them yet. Uh, so I haven't decided on office hours, but it will be some Monday, Wednesday, Friday though. Oh, discussions. Yeah, right. So your discussions are all on Tuesdays. When they happen is going to depend on your section number. So they either start at 1, 2, or 3, depending on your section number. It's 6 sections, I believe, split between 2 TAs. So each TA has 3 sections. That's going to be conducted via Zoom. Your TAs will post the Zoom links for those. So mostly the discussions are going to be group work that you're doing. There will be, it's not written on the syllabus, it's not included yet, but there will be some group work component for some of the discussions. So the discussions will involve, some small assignments occasionally that will be worth some points. Okay. So I'll add those to the syllabus a little bit later, either today or tomorrow. I'll add those to the weight. They won't be worth a huge amount, but it will be worth some non-zero amount of points arising from the discussions. But there's no like quizzes in the discussions, and there's no other kind of synchronous assignment in the discussions. The only thing is that occasionally there may be some group work that you turn in the discussion. So your TAs will take care of that, and you'll turn those in the exact same way. At the end of discussion, you would upload your work, right? So if you're assigned to a group and you have a list of problems to do, maybe you do like 2 of the problems and upload them. So all that will be taken care of later. So anyway, so we'll discuss that more later. Your first actual discussion is next Tuesday. So homework, yeah, I say roughly once a week. It's going to be more like once per week and a half is when you're going to have homework assigned. Exams and finals, so you're going to have 3 midterms and a final exam. Once I send out the lecture schedule, the exams will typically be posted like the day before or the day of, and you'll have a couple of days to do it. There's 2 MATLAB projects. Do you choose the groups? No. You'll be kind of basically when you're in your discussions in Zoom, you will be assigned some groups via breakout rooms, and I don't think the groups will always be static either. So you'll be swapped around a bunch. No, I'm going to start lecturing. It's just I'm going through everything, try to preempt all questions. Final is cumulative. Let's see, a couple MATLAB projects. The first one won't be posted until after your first exam, or actually after your second exam. So yeah, your first MATLAB project won't be posted until, well, right around the time of your second exam. Only going to be 2. If you've never used MATLAB before, don't worry, they're not going to be too hard. And I think that's about it. So I have the grade breakdown listed, and I have office hours. As I said before, I'm going to have a live stream once a week here, and you can swing by, ask questions in chat. I'll answer in chat. If I can't answer it in chat, if it's too tedious to answer in chat, I'll do it on paper. So that's how it's going to go. So any other questions before I start? Do I curve? I don't think I will need to curve in this. I mean, the grades are probably going to skew high. Everything being done at home means the grades will skew pretty high, so probably won't need to curve a lot more. There'll be a lot more natural A's than normal. So yeah, anyway, that's all that I can think of for now. So questions? Any questions before I start? Looking around. I think I covered everything. Okay. So this course is basically an entire course about a single equation. So my day has been great so far. I mean, I woke up at like 11:30, which is, anytime you wake up before noon is not ideal, but it's okay. Waking up at 11:30 is okay. So what should I say other than to say that this is kind of spoiling a little bit of the fun, but the entire course is about this equation. Okay, so this is the whole course. This is the entire course. Is that equation. So I guess we don't need to do the rest of the lectures. Okay. So what do I mean when I write out this equation? So this is a matrix equation. A is a matrix. X and B are vectors. But before we can talk about this, before we can get to talking about this, what I need to talk about is like where this stuff arises from. And so the basic example is when I have, say, the following system of equations. Okay, so consider this as a system of equations, right? So you did this forever ago in like second grade or something, right? So you have this system of equations. Asking for a solution to this system is asking for an x and a y that satisfy both of these equations simultaneously, right? So in this case, you might just look at this and say, okay, well, there's, let's see, the first one and the second one are both satisfied by x equals 3, y equals 2 is a solution. Right? So you can just check that quickly. So if x is 3 minus 2 times 2. So 3 minus 4, that's minus 1. Yep. But I have to check that it actually satisfies the next one too. So this is minus 3 plus 3 times 2. So minus 3 plus 6 is positive 3. Yep. So that works. Naturally, when you're solving any kind of equation, the answer is how many solutions do you have? So I've said it's a solution. But is it the solution? Yes, it is. It's the only solution. Well, geometrically, what did this mean, right? So geometrically, what this meant was that I know what these things are considered separately, right? So what is that? Ignore the second thing. What is that? That's a line, right? That's an equation for a line. So this is an equation for some line, right? Maybe, let's see, minus 1 is that one. So here's our first line. Here's L1. It's our first line. And then our second line is L sub 2. So this one maybe looks something like this. Okay. Now, I didn't do the greatest job of drawing those, but in this context, our solution here is that point of intersection, 3, 2. Okay. And so, geometrically, it was a lot easier to think about what it is that's going on here. This system of equations describe lines in the plane. And asking for a solution then is asking for when these lines intersect. Okay. Of course, that naturally means that thinking about it geometrically, this allows you to immediately characterize this into a couple of cases. All right. So what are the possibilities? In this case, I have one solution. Right. That one solution is the solution. It is unique. And the reason it's unique is because there's only one point of intersection when you have two lines that are transverse like this, right? So if you have two lines that meet, well, if they're two distinct lines, then they can only meet once. Now, I use the word distinct there to rule out one possibility. And the possibility I wanted to rule out is what if I had two lines and they meet, but they meet in infinitely many points? Well, then you might say, oh, those are the same line, right? You'd be right, But then you could say, well, how would that ever arise from some, from some equation? So what about the following, right? So let's say you have x minus 2y is equal to minus 1, and minus x plus 2y is equal to 1. Here is a system of equations. Okay. So there's a system of equations. Well, geometrically, what does this look like? Well, if I plot this line, right, then what I get is something like this. But what happens if I plot this line? Right, this is L2. They're the same line, right? And you can see that just by, you can multiply this equation by minus 1 on both sides. It's an equation, so that leaves it completely unchanged. So multiplying by minus 1 on both sides, you get x minus 2y is equal to minus 1. So it's the exact same line, right? So another way is that L sub 1 and L sub 2 meet in infinitely many points. Okay. Now, they are the same line, but in geometrically, considering this as a system of equations, what's another way of saying this? Like algebraically, what's going on is that any point that lies on the first line also lies on the second line. You can easily, you either believe this because you can just multiply both sides of the second equation by minus 1 to get literally the exact same equation. But if you don't believe it, coming from that, just pick a point on the first line and you'll see, oh, that point is also on the second line, right? So this means if my solutions arising here are points of intersection of these lines described in this way, if they meet in infinitely many points, it means infinitely many solutions to that system. Okay. All right. So we saw in the first case, you had two lines that met, but they were different lines. So if you have two lines and they're honest to God different lines, but they meet, what's the total number of points they can meet in? 1, right? That's the only option. So you have two lines, they meet at a single point. That's your only option, so you get one solution. If you have two lines that actually aren't two lines, but they're the same line, so they're two lines that overlap at every point, then they meet at infinitely many points, and so you get infinitely many solutions to this system. Right? And maybe you say to yourself, well, you're just being stupid here because you've just stupidly written the second line, in a way that's dumb and didn't immediately allow you to say that they're the same lines. But we want to include this, okay, in the cases anyway, and you'll see why later. So one more example then. Let's say x minus 2y is equal to minus 1, and minus x plus 2y is equal to 3. Right? What does this look like? Well, you might notice, okay, I can change this to actually make it immediately clear what it is that's going on here. All right, so these two systems are the same. So then I seek a solution, right, xy, such that x minus 2y is minus 1, but x minus 2y is also minus 3. Right? But the quantity on the left-hand side in these equations is the same. It's x minus 2y in both cases. So how can x minus 2y simultaneously be minus 1 and minus 3? It can't. Right? It can't. So what is this an example of? Geometrically, you could have thought of this example before even seeing a specific one. Geometrically, this is an example of parallel lines. Right? And so these lines never intersect, so this has no solutions. You see how I am very quickly moving back and forth between the notion of the algebra involved and the geometry involved, and then what this means for these solutions. So very quickly, I'm saying, okay, the number of solutions, or rather the solutions themselves, are the points of intersection of lines. So I could use the geometry without even referring algebraically to what's going on. Algebraically, looking at this, x minus 2y cannot simultaneously be two different values, right? That's one issue. So I can, before I even draw the picture, I can tell algebraically that's a problem. Conversely, before even looking at the equation, looking at this picture, anytime you have a configuration involving two parallel lines, they don't intersect. So if points of intersection are your solution, there's no solutions. Now, why did I go through all of this? You all knew this already. So why did I go through all this? I wanted to show that in this classical case of a system of equations where you just have two linear equations, you get this splitting of the cases into you have unique solution, no solution, or infinitely many solutions. Those three possibilities, okay? And the reason why I wanted to stress that so much is because that is going to be true for us throughout this course. So throughout this course, in all of these examples of equations that we talk about, okay, linear systems of equations, those are going to be the cases. You're either going to have infinitely many solutions, no solutions, or a single unique solution, okay? So even though as trivial as it seems in this case of doing this for lines, this is something that's going to be a recurring theme in this course. Okay? Now, in order to make our transition to being able to talk about systems involving more variables, instead of using x, y, and z, I'm going to move immediately. So I would rewrite this as x sub 1 minus 2, x sub 2 is equal to minus 1, and minus x sub 1 plus 2, x sub 2 is equal to 1. So I'm just going to put subscripts on the x here because that's a lot easier than trying to come up with new letters of the alphabet or using Greek alphabet or something, right? Okay, so a couple of things about terminology that I'll be discussing throughout the semester. So a solution to the system is, well, it is literally a list or an n-tuple, in this case an ordered pair x sub 1, x sub 2, that satisfies both of these equations simultaneously. The solution set to an equation like this would be the set of all solutions. So as we saw in these three cases, sometimes the solution set would have a single element, that'd be it. Sometimes the solution set will have infinitely many elements described geometrically. So in this case, that entire line of points, okay, forms the solution set. And sometimes the solution set will have nothing in it. So as a set, it will be empty. It will be called the empty set. We're not going to deal with that too much in terms of worrying about the empty set, if you're aware of all the stuff that involves dealing with the empty set. We'll talk about that stuff in chapter 4. Okay, so anyway. So two equations are said to be equivalent if they have the same solution set. That's important. Okay, so two systems of equations are said to be equivalent if they have the same solution set. Okay. So what is the purpose of this? The idea is that maybe the system of equations you started with was kind of nasty to work with, but if you could find a system of equations equivalent to it that wasn't quite so nasty to work with, then you could just solve that system and you would get the solution set to the original thing. Okay? All right. So, question. Note a system of linear equations has 1, no solution, or 2, exactly one solution, or 3, infinitely many solutions. Okay. Okay. So, more notation. A system of linear equations is consistent if it has either one solution or infinitely many solutions, if it has at least one solution, and inconsistent if it has no solutions. Okay. Now, before I write out like a general linear system of equations, here's a quick thing. Why are we studying linear algebra to begin with? Why is linear algebra something that people would study? Here's a common thing I've heard to describe linear algebra. One, it's the only branch of math that is 100% understood. Okay, it's being a little bit hyperbolic, but the point is that linear algebra is a highly understood subject. Okay, and as such, what that means is that typically, whenever you can take any problem in math that you're working on and turn it into a linear algebra problem, you are very happy. Okay, you are extremely happy in this case. In fact, like the computations that were done in my PhD dissertation would have been completely impossible were they not able to be formulated in terms of linear algebra and matrices, because this is basically one of the few parts of math that allow you to completely, or I'll say mostly completely, understand what's going on once they're turned into this language. Let's see here. The question is, so there'll be cases where we can find an equivalent system that will be easier to work with than the one given, yet will be equally valid to work with. Yes, indeed. That is exactly what we are going to do. We will be doing that almost immediately. Okay. So, this is inconsistent is what this says. It says inconsistent if it has no solutions. Very creative terminology here. Okay. And so, what does a general system of linear equations look like? So maybe it looks something, like this. Why did I do that? And the next line would be A21 x1 plus A22 x2 and so on. A2n x sub n is equal to B sub 2. And then it will continue on in that fashion until we have A sub n1 x sub 1 plus A sub n2 x sub 2 and so on to A sub nn x sub n is equal to B sub n. Now, if you're confused by these double subscripts, don't worry about it right now. We'll talk about it more later. This is just my way right now of writing out what this completely general system of linear equations might look like. Okay. Why are these called linear equations? Well, the only powers of x here, the variable showing up, is 1. Okay. Now you might try to fight me there and say, what if I had an equation that had x sub 2 times x sub 1 here? Is that still linear because the powers of x sub 1 and x sub 2 are both 1? No, because x sub 1 and x sub 2, since they're both variables, are considered separately to the first power, but multiplying 2 together, that would be a second order term, because both those x's, those x sub i's are both variables. That would be an order 2 term. That's not allowed. So you might say, why do we study linear equations? One, they're a lot easier than nonlinear equations, but the main reason why in all courses, whether you're talking about 246, differential equations, whatever, The reason why linear is an important thing is that it allows you to systematically describe these things. If I allowed nonlinear here, the set of equations I can study is so vast and so huge, and the behavior is so wild and different between each case that they basically have to be considered separately almost. So the idea is that linear equations, though, these are of this particular form, and they're exactly, I can study them, as a whole all at once. Okay. So here's a particular example. Here's a system. Say x sub 1 minus 2, x sub 2 plus x sub 3 is equal to 0. That's our first equation. The next one is 2x sub 2 minus 8x sub 3. That is equal to 8. And lastly, 5x sub 1 minus 5x sub 3. Of course, I've written it strangely because I want to line them up. Okay, is equal to 10. Okay, so note how this fits into the previous method I have of writing this. Okay, now what I want to form, we'll get into this more a bit later. So what I want to form is the coefficient matrix What is the coefficient matrix? The coefficient matrix is a rectangular array of numbers that are the coefficients on the variables here arranged in this way. So the coefficient matrix consists of these coefficients that I can just read off, row-wise or column-wise, however you want to do this. So this would be 1, minus 2, 1, 0, 2, minus 8, 5, 0, minus 5. That's the coefficient matrix. Okay. In this case, this is a 3 by 3 matrix. When we write this is rows by columns. That is how matrices are written. So number of rows by number of columns. So this is a 3 by 3. It's called the coefficient matrix. There is also the augmented matrix. The augmented matrix is like the coefficient matrix, but I have tacked on an extra column here. And that extra column I've tacked on is the right-hand side of this equation. So the coefficient matrix encodes all of the coefficients of these variables, but looking at the equation, that isn't all of the data. The remaining data is over here. Now you might say, wait, you didn't include the actual variables themselves. Well, the variables are going to be always the same. In a system involving however many variables you've decided it involves, then the variables are always going to be x of 1, x of 2, x of 3, up to x sub n, right? So then it's the coefficients that are all you need to keep track of on the left-hand side. But on the right-hand side, you have these other numbers here. And so the augmented matrix actually keeps track of absolutely everything from this system. So if I write out the augmented matrix, it's just the coefficient matrix with that extra column tacked on. So I'm even going to write it like that because you will see it written in this way. But functionally, there's no... I'm going to do this. This is the only time I'm going to do this. From now on, I'm just going to tack on this extra column. But you might have seen it written like this before. So this is the augmented matrix. Okay. And note that there is a one-to-one correspondence. Whatever this system was, I have encoded literally 100% of the data from that system of equations into this augmented matrix. Okay. What is the idea? The idea is to solve a linear system by conducting algebraic operations on the equations involved. Okay, which is easier to keep track of in the augmented matrix. It's easier to keep track of by doing computations on the augmented matrix itself. Okay. All right. So that is the idea. Now, in order to try to be efficient with this, and we'll do this during lecture on Friday, what is the idea here? So the idea is that to help in this, there are the elementary row operations. Okay. Okay. So what are the elementary row operations? There are 3 of them. So we will solve a system using these 3 on Friday. So one is replacement. Okay, this is very important. So this is replace one row by the sum of itself and a multiple of another row. We'll talk next time about why this is something you should be allowed to do. There is interchange or swap. Okay, you can interchange, can swap 2 rows. So pick any 2 rows you want, you can swap them. And lastly, you can scale an individual row. So you can multiply all entries in a row by a non-zero constant. Okay. Okay. So, quick question to explain. We're out of time, but just quickly, what do each of these things do in the context of an equation? So let's think about it in the context of this equation, right? So replacing one row by the sum of itself and a multiple of another row. So let's just take that multiple to be 1 for a second. So replacement where I've taken one row and I've just added to it another row and I have then replaced it. So in the augmented matrix, okay, a row is really just encoding one of these equations, right? So when you say row, a row in the augmented matrix is one of these equations in the system. Okay. And so say replacing the second row by the sum of the first 2 rows is replacing the second equation by summing these 2 equations. But if you look at this and you thought of how you did Gaussian elimination when you first were introduced to systems of equations, if I'm adding these 2 rows, you might think to do that, for instance, because there's a minus 2x sub 2 here and a 2x sub 2 here, so you're getting rid of the x sub 2 by adding these 2 rows and replacing it. You're taking 2 equations, two statements, this thing is equal to that thing, this thing is equal to that thing, and you're adding them, and then you're replacing it with the result. You can do that, right? This is something you can do from algebra. This is something that's not going to alter the solution set at all, right? And ultimately, that's the point, and we'll talk about that. Okay, so then the interchange, the swapping of 2 rows, would just be writing this system in a different order. It would be, instead of listing this as first, second, third equation, I've just swapped the order of the equations. That clearly doesn't change anything about the system. Okay, and then for scaling, I can multiply all entries in a row by non-zero constant. Okay, so that is me looking at one of these equations and saying I can multiply any of these equations by whatever non-zero constant I want. If I multiply by 0, then I'm basically negating all of the info that came from that equation. What I said in this is multiply all entries in a row by a constant, if that was the confusing word here. So all entries in a row are multiplied by a non-zero constant. So for instance, if I look at the second equation and I want to multiply by the constant 1/2, right, 1 over 2, then that would be me replacing this equation, 2x sub 2 minus 8x sub 3 is equal to 8, by x sub 2 minus 4x sub 3 is equal to 4. That's the same equation, right? And so that doesn't change anything. The idea behind these is that if I'm doing these elementary row operations, I'm changing the system that I'm dealing with, but I'm not changing the solution set. So ultimately, that someone asked the question, are you going to take, linear system and turn it into something that is different, easier to work with, but has the same solution set? The answer is yes, and this is how we're going to do that. Okay, so we'll do an example of this on Friday. You are going to be doing this a ridiculous amount this semester, so you have to get used to doing this quickly, because in the early parts of the semester, I will be doing these in the example step by step, and then suddenly, magically, one day, I will never do that again. So magically, one day, every example you see, I will start with a matrix, and then I will do all these off paper and immediately get the answer. Okay, so you have to practice this a lot. But anyway. Okay, so that is it, I think, for today. So I don't have another class today, so I can typically stay a little bit longer for you guys to answer questions. Let's see here. So I don't have any. I will do this example next time. So the same example that we did, this example I'll work through at the beginning of lecture next time, and then we'll do a bunch more examples like that. Yeah, reduced row echelon form. That's what we're doing. Yeah, so we'll talk about row echelon form next time as well. So anything else? Yeah, we'll see. Maybe we need mods, but it happened in 246 as well, and I only had to ban someone once, and then it stopped. So anyway, okay. So I think that's about it. So I will see you all on Friday. Like I said, I will post the announcement for the lecture on Friday. I'll continue to do that for the first couple weeks of classes, and then after that, I'll just expect you all to show up whenever lecture time is. So anyway, that's that. So I will see you all on Friday.